All right, and now I am going to show everyone a different kind of application of tangent line. And again, you're going to see why tangent lines are so important. It's not just a problem we're doing for fun. It's not only some geometry problem to be done out there. It has such a large and diverse amount of applications out there. Okay, so what I'm about to show everybody here is the skill of how to find, or just this skill here is called the linear approximation. Linear approximation. All right. And so to get into understanding this, and this entire lecture is all about a technique, a method. So it's a step-by-step procedure, because it's an approximation method right here, and you will understand what it means by linear later on. But approximation is the idea right there, and so anytime it comes to approximation, then it's just simply a step. It's a step-by-step procedure that we do to get our best approximation of a value. Okay, and so now I am again going to erase the title of our discussion topic here, and let's get to it. I am going to introduce a problem, a promoting problem, a problem that promotes the idea right here. Okay, so let's say I am going to ask anyone, and as you view along with my video over here, feel free to pause the video and do any of your math if you need to. But how about the problem I want to bring up here that can challenge anyone is to calculate, okay, the square root of 4.5. That's easy. I mean, what's hard about calculating the square root of 4.5? So I'm pretty sure that once you see me writing this, then you're gonna pause the video and rush into using your calculator and do a square root of 4.5. Yes, I believe so. But so here's the thing. Believe me or not, there are still a lot of calculators out there do not offer the square root operation. Okay, I mean, there are still people who doesn't have who don't want to buy the kind of advanced calculator, so they stay on the very basic calculator that comes without square root. So I just trying to point out the desperate situation where we don't have the square root operator on our calculator, and besides forcing the calculator, even if you have the square root operator, the operation on your calculator, it's still, to me, I call it's a brutal math to force the calculator to do this kind of works right here. So here's the thing. So now I'm bringing you into that scenario, like, hey, what if we cannot use the square root operation on your calculator? Because think about that scenario where your calculator doesn't have that operation to find square root. Then that doesn't mean we're gonna give up. We're just not gonna give up with any problem. The whole reason I'm having a video here, because there are things that we just can't give up, and we gotta find a way to overcome. So calculate now is not the precise terms anymore, because I put you in that situation where we cannot use, or we don't even have the operation. Think about that. We don't have the operation for calculating square root. So calculate to get the exact answer, there's no luck. Okay? Then I'm gonna switch to, in that case, we're gonna switch that to a different plan. How about we approximate? Okay, how about we approximate? Okay, so approximate just basically means we get the closest answer to the real answer as we can. Okay, and that's what approximates means. And so here's the thing. And again, keep in mind, we don't have the square root. Pretend that we don't have the square root operations on our calculator. And so how do we approximate? So, because here's the thing. If I'm asking calculate what square root of 4, easy. Nobody needs the calculator for square root of 4. It's 2. Okay? Yes, that's it. But now square root of 4.5, naturally anyone will start thinking of using a calculator. And then if the calculator doesn't have the square root operation, we need to approximate. So this is what I'm doing. I am going to, I'm going to ask people to follow along with me, and I will explain the reason how I got this. How about from where 4.5 is? Okay. Your calculator should be basic enough to do this for me. Multiply with 1/4. There you go. This is what even the most basic calculator can do. Even if you don't know how to operate with fraction on your calculator, it just means 4.5 divided by 4. That's what it is. Your calculator, no matter how old school, how old-fashioned your calculator is, you can still do this with your very limited calculator. Okay? And we're going to add 1. Okay? And of course, adding and subtracting, multiplying and dividing are all basic features of any calculator, no matter how old-fashioned your calculator is. Okay? And so in that way, go ahead and do the calculation. 4.5 divided by 4. 4.5 divided by 4 is a 1.125. Okay? And adding 1. And so that gives me, and here I'm showing the little step-by-steps in our approximation, so it still takes me some time, but your mind should be fast enough for 4.5 divided by 4. You can even do mental math with this. And add 1, so your answer here is 2.125. Okay? So ladies and gentlemen, now I announce to you that the actual answer of this square root of 4.5 can be approximately close. That's why I'm saying we're only approximating. Okay, but the true answer of square root of 4.5 is approximately 2.125. Okay, so I'm not saying that this is the exact answer, but this is an approximate. Let's find out how close it is. And so now with a calculator like about standard, like a TI 83 or 84 calculator, or even now in your some of your later operating system with iOS, then your iPhones there can handle square root operations. So let's find out right here. Now this time I'm saying that I'm about to do the real calculation on the square root of 4.5 right here. So now taking square root of 4.5, my answer on the real square root. So the approximation work here is done. Okay. Now I'm going to have to highlight what I'm about to write on the board here. True answer. Okay, true. The true value, the true answer. The true answer of square root of 4.5 is 2.12. Okay, 13203 and a lot longer. Okay, but so now as far as rounding down to, well, going in this approximation method, then we are forced, we have no choice rather than staying with 3 decimals is the most, right? And so in 3 decimal places, let's say if we take this true answer, round it down to 3 decimals, and we're looking at an answer being 2.121. Look at how far off are we? The approximation value, the approximated value is only off by, so we're only off, okay, we're off by, just see, our approximation is only off by 0.004 here. And that's actually pretty good, right? It's a pretty good for an approximation right there. We're off by just 0.004, and we're a little bit above, right? Very tiny amount being above the true answer. Okay, so how did I do that? How did I do that? And this is now I'm about to explain. And then it gets to the step-by-step work right here. And so now as I go through the explanation, I will highlight a couple terminology so that, no, don't look down to this method, this technique I'm showing you, any one of you, because trust me, some among the viewers today, some of you will one day decide to go into a professional mathematical career where your entire career there is to work on approximations. There are PhDs out there who spend their entire life working on different techniques to approximate. And this kind of problem was once also a famous problem among the ancient mathematicians. So don't look down on whatever you're learning here. It might be a small step, which is only a small stepping stone, but it opens to the idea. And by the time that if any of you arrive to Calc 3, you're going to see a lot of this idea come back already. Okay? And so now, how did I do that? So I already showed you the answer, and I briefly did that, but a lot of mysterious thing came out along the work right there, and I'm sure you have a lot of questions, like say, for example, what I did was a 4.5 times a 1 point, times a 1/4 y, okay, and then plus 1 after that y, okay. So this is now y. So first up, so yes, we know that we need to approximate square root of 4.5. And so notice, one thing to notice, a couple of things to notice. See, it's the whole, at this point, anyone viewing the video here is mature enough to understand that a lot of our operations came out from a function. A lot of our calculating operations came out from a function. Well, what do I mean by that? Well, if you take a tan square, okay, this squaring is an operation because you had f of x equals x squared function. It's a function, and the function here is corresponding with an operation. And so in that way, when I'm explaining, then square root of 4.5, the operation square root right here, we can think about there exists a function square root of x. Okay, so taking square root is the same as we having a square root function, square root of x. And so taking square root, this is what we realize right here, what we notice. Square root of 4.5 is the same as, so here we just simply define, right? We define f of x to be square root of x, and so square root of 4.5 is exactly the same as f of 4.5. That's one thing I want to trigger your attention to that, your awareness to that. I want to raise your awareness on this. Okay, so taking a square root simply a completely an operational problem, but it turns out to be just simply a function, a square root function that after we define, and then we are evaluating that square root, meaning we evaluating the function at that given value. Okay, so that's one thing we noticed. And now another thing to notice, so that's one bulleted point to notice. Another thing I want to raise your awareness about is that isn't 4.5 so close? Okay, so 4.5 is close to 4, am I correct? Okay, and when I'm asking this for video viewers out there, when I'm asking if I'm correct, feel free to pause the video and think of what I mean right here. It's close enough. It's about only 0.5 away from 4. But why do I all of a sudden out of nowhere mention about this value? Simply because, well, 4 is close enough. And 4 is an easy value to substitute. I mentioned it. I mentioned this a moment ago. Did you need a calculator to get this value? No, it's this value when you substituting it into your function, it's so easy. It's so easy to the point that you don't even need a calculator. Okay, even your mental math can get you through with that. Square root of 2. So basically, with the two things that I pointed out here, it's what we need to notice here is first, the problem we're operating here came out from a function. That function we can call that as a square root function. Okay, and then the value that we really are attempting to find the actual calculation here is close to some what I call now. It's actually kind of like my term over my years of teaching this kind of stuff. So I developed this term right here. This is called the easy point. The easy value. The easy value where either you are using the calculator, it's not going to cost too much calculator memory, like the calculator strength. It's not going to cost too much calculator strength. It's not going to cost too much brain power. So either way, you're still going to get an easy calculation on a value like this. That's why I call it easy value. So the point is we are trying to approximate a value, but good news enough, it's close to some easy value. It's close to some easy value. Okay, so that's all I'm raising that's all I need to raise your awareness for. The square root problem came out, the square root operation came out from a function, f of x equals square root of x. And further, this value that we are evaluating is close to a value, and actually we can choose this easy value as well. So I chose that simply because it's close and it's an easy value. Okay, and so now here's what I'm doing. All right, so in my work here, the real actual step now is that once we realize that our function, and just earlier I was saying that it's something we notice, but now we're going to take that as a formal understanding. If we can define a function being the square root of x, okay? If we can define a function being square root of x, then our derivative, I am going to find our derivative. The derivative of square root of x, and at this point, anyone learning this video lesson must be learned after anyone is fluent with all your skills in finding derivatives, okay? At least all the basic power rules and all that. So allow me not to go too far back of how to find the derivatives. This derivative here is simply just a 1 over 2 square root of x. Feel free to pause the video, get your own papers and pencils out, and do find your own actual derivative, and to make sure you agree with my answer here. Okay? And so that's my first step right here. I found the derivative of our function where did this function came from? It's something that we recognized from our operation right here. Our operation is taking square roots, so we had that function here defining the square root problem. Okay, it's a f of x equals square root of x. And so first step into that, we get the derivative. Okay, and so the next thing now is I am going to actually, the next big step here is I'm going to get the tangent equation. Okay, the tangent line. That's the next big step right here. Get the tangent line equation at x equals 4. Okay, at x equals 4. You might feel shocked about the plan I'm writing down right here, but yes, everybody at this point is so familiar with getting a tangent line equation, but why at 4? Why is it not at 4.5? Why is it not at 4.5? You will see that reasoning later on, but now what I need you to notice, I'm trying to obtain the tangent line at that easy value that I was saying. 4.5 is close to this easy value. Okay, so here's the advantage of using this easy value. This is the easy value, but good news, it's close enough to 4.5. Right? So I gotta make it clear again. We need to get the tangent line equation, a complete mx plus b, right? The y equals mx plus b, but at this easy value. And the easy value, where did that come from? I already raised your awareness earlier. This actual value we're attempting is close to this easy value, and this easy value is easy in a sense that you can easily substitute that in here and find square root of 4 easily. You don't even need a calculator for that. That's my point right there. All right, so now let me switch to the other board and again repeat the procedure of finding tangent line, and you can do together with me as well independently. So that means the slope of the tangent line is from where your derivative is 1 over 2 square root of x, but now I'm going to substitute in 4. The easy value goes into your derivative to get the slope of the tangent line, because again, as I was also being clear earlier, we want to get the tangent line. We want to get the tangent line equation, but at this easy value, not at 4.5, not at our main target. Okay? And so in that way, the slope here is going to equal 1 over 4. You see, when it gets to this, I've been going completely without the calculator. Why is that? Because 4 itself is so easy that getting square root of 4 is quickly a 2, and 2 times 2 is a 4. You get a slope 1/4. Okay? And so now, with your tangent line equation, now we need the tangent point. So again, in case anyone's still going a little loosely with this, then tangent point is from where x equals 4. We're going to substitute. See, we're going to find the y value. And I should have written that in the same line right there. But this is tangent point, t points, tangent point. Okay, forgive me if I'm using shorthand notation for that. But so y value here is going to be square root of 4. I'm substituting our easy point, and the tangent points also came out right from the easy point, the easy value. So square root of 4 is a 2. See how easy that is? I don't need a calculator for that. Okay, so the tangent point here is completed at 4, 2, incomplete point like that. But now getting the tangent point, and again, ultimately, as the big step, I'm trying to get the tangent line equation, or the equation of the tangent line at that easy value, the x equals 4 value. I'm on my way getting there, very close now. So your tangent line equation, starting out with the point slope equation, allow me to pick up the little space here at this point. Y minus 2, the y value of your tangent point, because the tangent point stays on the tangent line and stay on the curve. So y minus 2 equals 1/4 the slope times x minus 4. See, 4 and 2 are your components of your tangent point. And I'm using this point slope. Once in a while I switch to a different style. Usually this is not my style, but admittedly here it's faster a little bit. So now distributing that 1/4 over, okay, and then adding the 2 to the other side, my tangent line equation. Slope 1/4, okay, x plus 1. Okay, so now here's the thing. Did you notice in my earlier work, let me recall a scratch work, what I did in my approximation was 4.5, I multiply with 1/4, okay, and I plus 1 and I added 1. You can roll back to the video and see how I did that earlier. Plus 1. Okay, so the truth here is, this is the truth. The plan so this is the equation of the tangent line at the easy point. So the plan now is that I now created a new function. The tangent line equation in the end is another linear function. It's a linear function. Your actual function here is a non-linear function. It's some square root function. But then at this easy point, x equals 4, we can create the equation of a tangent line and treat that equation of the tangent line as a linear equation, t of x to equal 1/4 x plus 1. Okay, it's a linear function. Okay, it came right out from your the tangent line equation at the easy point of 4, 2. 4 is the easy value that I chose earlier. And now, once we've had our tangent line equation, but now regarding it as a function, as a linear function, then now I can use a t here instead of substituting 4.5 into the original function. Instead of substituting directly 4.5 into f of x, that's too brutal. I'm in the way how I see it. We force the calculator to overwork. Okay, even if the calculator is having that feature, or in the worst case we don't have the square root operation on your calculator, then we can use this equation of the tangent line. And again, this equation of the tangent line came out from the easy point that anyone can obtain. Okay, and then we use that equation of the tangent line and substitute in 4.5. So that's what I did earlier in my beginning demonstration. So t of 4.5 equals 1/4 multiplied with 4.5, okay, plus 1. And that's how I did that. And then that's now gave me the answer being 2.125. And we only missed the real answers, about 0.004 right there. Okay, and so this at the end, this tangent line equation that we now regard it to as a function, as a linear function. Formal term, we call this tangent line function right here, it's the linearization. Okay, it's the linearization at x equals 4. Okay, so now the entire picture is that when we are asked to calculate a value using some operations that may be challenging on the calculator or challenging for your own mental math, then we're going to first realize a nearby value. So we're going to first recognize a nearby value. So 4.5 is near 4. And 4 here, there are so many values nearby. You got to keep that in mind, but we purposely chose a nearby value that's easy under this operation. You got me there on that. So 4.5 is near 4, it's near 3, it's near 4.01, it's near 0.4.1. But we chose 4 simply because 4 is near, and being near and easy inside of that operation. Okay, so that's one thing. And so now once we recognize that, we chose that point, then we're going to go ahead and define our operation here as a function. Then the first big step, get the derivative of that function. Because the derivative of that function, using this easy point, it's still going to give you an easy way to calculate slope of the tangent line. And so in that way, the next big step is to get the equation of the tangent line at that easy point right there. And then ultimately, the usefulness of the tangent line, now is that once we've had the tangent line, and you see I keep emphasizing the term easy point, because see that point, I went through all of these steps completely without the calculator. And so when we came to the actual equation of the tangent line at that easy point, not the real value 4.5 that we were doing, this is the equation again, the equation of tangent line at the easy point. And so we can use that equation of a tangent line, which is only involve linear operations. I'm using the term linear operation now, meaning we only need to either multiply, divide, or add or subtract, which is all those basic features with any even very limited calculator. We use that to substitute the actual value, and now we can use the final answer here as an approximate, something close enough to the real answer. Okay, so now the new term here, that this equation of the tangent line that we now regarded as a function, as a linear function, we call that it's the linearization for this function square root right here, but at the easy value x equals 4. Okay, and so now before I'm heading out into some real example, some actual example, and it's pretty much along with this kind of approximation problem again. It's just giving anyone more opportunity to grasp the entire picture again. But now, before I'm moving out to another example, let me bring you into an actual graph to demonstrate what was going on here. You see, this is your square root of x function right there. This is your square root of x. This value here is that value that we're of our target right there. And let me zoom it in. See, it's right at 4.5. This value is right at 4.5, and even machine can only round to 3 decimals. Okay, even machine can only round to 3 decimals, and it's meant to be, you see, the 4.5 and this value right on the curve. And this is, by the way, our graph of the square root function. And so 4.5 on the curve is this value 2.121, and that's exact value. But now, okay, and so this point in black here, and let me zoom in, and no matter how far we zoom in, we still can't tell the difference too much, and that's the good usefulness about so the easy point is when x equals 4, into the function itself, square root of 4 is 2, and that's so easy that we don't need machine for that. Okay, and so look at how close in terms of these 2 points right here. Look at how close that is. 4.5 for x of the blue line, of a blue point, is only 0.5 away from this easy value. So easy value is not our real target, but now at least I am going to build a tangent line. And let me also use a black color for the tangent line right here. You see, and so vertically as a y value, right? All right, so maybe let me put it in thinner weights right here for you to see. But if we're using 4.5 substituted in, and now in a green version, Okay, I just now put in a green version, supposedly. So now let me really have to zoom it in. So this black point is the tangent point, came out from the easy value on our curve right here, where the tangent line is right at that point 4,2. But now on this graph right here, you see even my machines, my decimals I'm using having pretty good precision, but we have to really zoom it in to see the difference. So 4.5 being substituted directly into the function gives me a value right here. Okay, but 4.5 substituted into our linearization, the t of x function. So this function right here is the famous 1/4 x plus 1 from the lecture that from the step I was doing earlier. So this point right here is 4.5 comma 2.125. This is t at 4.5 right here. So the point on the black line and versus the actual value is here. So see how close that is. I already had to zoom in a lot to just barely see some difference between the two. And now when we zoom out enough to see the entire picture of the graph and the tangent line, then you see the green points and the blue points are completely, mixed together that nobody can really see anymore. Okay, there are actually 2 points there. So if we need, and that's the whole point of how usefulness using a tangent line. So we use a tangent line from an easy point, shoot out a tangent line, and once on that tangent line, it's being a linear, containing only linear operation, it's a lot easier to calculate the value. But we use that values as an approximation to the real value. And look at how close we can get. See, from here, right here in this picture, when I'm putting up the two graphs together and just try to see an actual picture of the two graphs, the tangent line, the graph of the tangent line, t of x equals 1/4 x plus 1 is here, the black line, and the actual graph of of square root of x is in the red one. Then the approximate value in green and the real value in blue, we can't see the difference. Okay, and so that's the idea of doing linear approximation. We use a tangent line at a nearby value, okay, and treating that as a function, to approximate our target value right there. Okay, so now we are ready for a couple of other examples. Let me now spend some time erasing the board here. All right, so in this first example, let's call it example 1. And so does it matter how many examples I give here? It could be only 1, it could be only 2, or it could be more than that, but pretty much any problem is one problem standing on its own right there. Okay, so I can utilize that same function. How about we want to approximate? Okay, and of course now you understand what I mean. We use the linearization. We use the linearization to approximate square root of 10. Okay, 10 is a whole value. 10 is a whole value, but unfortunately, taking square root of 10 is not that simple at all. Okay, but so that's why, and like I said, let's give up the idea of how brutally plugging it into the calculator and get an answer. Of course, I mean, calculator is strong enough, can handle that, but that's not the point of this example. Okay, and besides, still think for the people who cannot afford getting an advanced calculator like that, then they stay with the very basic one from a supermarket cashier machine or something like that. Then those machines don't really have a square root function. Okay, because they don't have an application for square root out there. And so now our first job here is to recognize. So to approximate this, then we can see that we can define, right? We can define f of x to be a square root of x function again. Okay, so that's how now I'm already getting into it. And after we define that, then we can see that just kind of like a checkpoint right here. Then that means square root of 10 truly is, or in precise term, equals to f at 10, or square root of 10. I don't even think I have to write that. So square root of 10. The reason I'm writing it this way, square root of 10 equals f of 10, means I want viewers to see square root of 10 as the function that we defined here previously, substituted in x equals 10. But see, in the end, if we're doing this, then we're just beating around the bush. As I said, we only forcing the calculator to overwork, but unnecessary. And so, realizing that this is not easy to do, right? We're gonna now need to recognize an easy point. An easy point here, see, look at observe our operation again. It's a square root, so I believe, for any viewers who following with this video, I do believe there will be some easy point close enough to this that's easy for your own, even mental math. So trust me on that. So, I hope you see what I'm thinking. I hope you understand, I hope you think with what I'm thinking. Isn't the easy value here? Isn't the easy value that we can choose? See, it's our choice. The easy value here, it's most reasonable to choose x equals 9, right? Why is that? Well, it's being 1 away from 10. So 9 makes a difference, 1 with 10. How close that is, we're not really judging, but it's close enough so that, here's the thing. What's the good usefulness of this? Think about square root of 9. Do you need a calculator for this? Okay, no, it's just simply 3, right? The next easy value substituting in the square root would be a 16. So why not choosing 9? Because at least 9 is closer to 10 compared to 16, right? This is also another easy one. Square root of 16 equals straight out of your mind right there, without calculator, 4. But too far away from 10 compared to 9. Okay, and so that's the reason why I'm choosing 9 as an easy value, close enough. And I'm not saying, I'm not making judge about how close it is good. It's just close, about the best one we can find. Okay, so now that easy value here is x equals 9. So now our plan here is we already had the function defined. The big plan here, first step, okay, get f prime. And that's the whole point of spending our time learning about all different techniques for getting derivative. So it's still that standard function as I used in the promoting problem, the introduction problem. So here it's still 1 over 2 square root of 2. That's our general derivative. And so from that point, the next big step here is to get, okay, the equation of tangent line. And here, again, in my role here on the board in front of the camera here is to show people steps. So that's why I'm going, and you can feel that it's slow, but when you're actually on your own doing this, on your own paper and pencil, you don't need to write down all these things, just these are your planning. So it's going to be a lot faster than what I'm doing here compared to the pace I'm doing here. So now we get the equation of tangent line, but critically at the easy value, x equals 9, okay? X equals 9, not x equals 10. X equals 9. All right, and so now I am going to navigate to my other board. And I'm going to spend a little bit of time erasing my board first of all. Okay, so now from that clear understanding of, and clearly knowing what our plan is, from where the derivative is, I'm going to substitute in the easy value into our derivative. So 1 over 2 times square root of 9, that gives me a 1/6. Okay, that's an easy fraction. So that means now in our tangent point, our t point, our tangent point, okay, and of course we're finding the tangent point at x equals 9. So when x equals 9, and that means the y value, and this is just repeating of our previous understanding. So we take the value here for x, substitute that into the beginning function. The original function, not the tangent line, because we haven't even found the equation of the tangent line yet. And so we substitute the given value right here, the easy value, into the equation of the original function. And so now it's square root of 9 right here, and that is 3. So my complete tangent point is at, in complete form, 9, 3. Okay, so 9, 3, so that means now on my way to find the actual equation of the tangent line. I'm sticking with point slope again to keep things a little speed up right there, a little sped up, but y minus 3, because this point for sure stays on the tangent line as well. So that's why we can use a point slope. We already found the slope being 1/6. So y minus 3 equals 1/6 times x minus 9. So 3 and 9, or 9 and 3 came out from the tension point. Okay, so this is your point slope equation of the tension line already. But I want to purposely write that in the form of y equals mx plus b. So that means y equals, I'm going to distribute that 1/6 to each term right here and add the 3 over. So now we're looking at a 1/6x, right, plus a 3 half. All right, and so now that's your equation of the tension line. And so now we can start writing that as some function t of x. Think of this as some tangent function, okay? A linear function t of x equals, now 1/6 x plus 3 halves. So again, I just need to remind, I have made this term before, but this t of x right here, this linear function t of x, it was our function, our equation of the tangent line, but now we see that we purposely regard to that as a linear function. So this linear function has a name. We call that, this is the linearization. Okay, the linearization at the given value x equals 9 at the easy point. Okay, the linearization at x equals 9. But now the good usefulness now is that now I can say square root of 10 instead of getting the exact value. Nope, we're not going that way. We're not going to rush into substituting that into the f of x function, because this is what f of 10 is, but we don't want to go that way for getting the exact value. So I'm going to sort of like play a workaround. So this is going to be 10 is the value, but multiply with 1/6. Okay, so I'm not going to say equal. It's only approximate. It's only an approximate. So square root of 10 can approximately be calculated by 10 times 1/6 plus 3 halves. Okay. Yes. And so, yes, it might take a little while, a little work right here, but again, put yourself in the situation that if your calculator doesn't have the nice square root operation, then at least it still saves you, because you can still do these with your basic calculator. And so overall answer in decimal comes out being, so this approximation here came out being 3.16. It's technically 1.66666 with all the repeating 6 right here. And in 3 decimals, you can call that 3.167. Okay, 3.167. Okay, believe it or not, square root of 10 is approximately 3.167. Let's see how happy we can be with that. Okay. Now I'm getting back to my board on the computer, to my board here. I want to retain all this work here because I want to, actually now let me erase all this work we have had here, because we already have done that. So back to this point right here. So the real value from the calculator, real value in 3 decimal places, rounded down in 3.162. Real value, if we really use a calculator, some advanced calculator with the square root operation, 3.162, or a lot longer, but usually we stay with 3 decimals. And so now, using the approximation, we got square root of 10 using the linear approximation, using the linearization at x equals 9. And we're looking at square root 10 can be approximated by 3.167. How far off are we? We're only off by 0.005. It's not so bad. Okay, and so that's the whole point of that's the whole usefulness of using the linear approximation. And now, why is it called linear approximation? Because we use a linear function. Okay, so now the whole title of the entire discussion topic was named linear approximation. We'll know that we're approximating square root or any of these function value, but why linear? Because ultimately we use the equation of a tangent, which is a line, which is a linear equation, a linear function. To make the whole point of linear function is it's making calculation easy in a sense that it only involves adding, subtracting, multiplication, and division. Okay, and that's what it is. So using a linear function to approximate a supposedly complicated value on some complicated function. So I see this as complicated function, but we use linear function to approximate, and we get pretty close answer. And that's why I'm calling that it's a linear approximation technique, a linear approximation method right there. Okay, so let's try another one right here. And this problem is particularly good for any of the viewers, any of the students of mine who are planning to go into physics right here, and I mean who are planning to study a lot with physics. Then eventually somewhere here and there you will see this kind of value. All right, so in example 2, again, so I've been staying with 2 problems, including the introduction problem dealing with square root, and the example 1 just now it's on square root function again. So you might formulate into your mind that this technique is only good on square root function. Not really. It's good on any function, So that's why I'm introducing now this next problem. Very similar kind of problem. We want to approximate. Okay. Sine of 0.1. Sine of 0.1. Sine of 0.1. Another note right here. That value right here is in radian. Okay, so that value 0.1 is a value in radians. It's not like a 0.1 degrees. It's not that. This is 0.1 radians, meaning whichever value times with pi. Pi itself is a 3.14 and a lot longer. So whichever that coefficient in front of pi that compensates overall to be a 0.1. Okay, so it is like a 1/30th of a pi, right there, something like that. A pi over 30 is about this 0.1 right here. But in the end, we want to evaluate. So we think about ancient calculators back then. They don't have the sine function on them. There are still calculators existing out there that comes without the calculator, the sine and cosine and trig functions. Okay, and so if we're asked, and if you simply have those calculators and being asked to find sine of 0.01 right here, then we give up. But no, that's not what we want to. We have to find a way to overcome with the problem. And so here's the thing again. So evaluating this means things came out from a function. So we can realize that our function here we can define a function being f of x as sine of x. That famous trig function that everybody has seen right before prior to entering calculus. Okay, so f of x is sine of x. And so from that point, now the next thing to realize is 0.1 is close to, okay, close to what? Remember the idea, the strategy, the strategic plan in the earlier 2 problems. We want to choose a point close, and really we're not aiming at judging how close is good to be close, but it's about close and easy to be substituted into the function. Okay, to be substituted in a function. So 0.1 can be closed with 1. Okay. It's close to 1, and 0.1 is close to 0. Okay, which one is a better choice for us? They're both close, and of course 0 is closer. Yeah, I agree. And 0 is easy to be calculated in the sine function. Instead of 1. 1 is close to 0.1 as well, but 1 is not that easy. So sine of 1 is still in the end not that easy to calculate it, and provided these are all values in radians. This is 0 pi, this is about 1/3 pi, something like that. Okay, and so now I'm going to purposely choose, and like I said, we chose with a smart plan right there. So 0.1 is close to 0. Okay, so keep that, or to be precise, 0.01 is close to x equals 0. So we refer to this as the easy point, because I just now made my quick verification that the sine of 0 is an easy value to obtain. This is an easy value. Okay, and so now, once again, once we have identified those two key ingredient factors like that, then here's how I'm tackling down the problem. Well, big first step, we need to get f prime. Okay, and f prime of x is a simple one in this kind of problem. F prime of x with f of x being sine of x, and f prime of x is simply cosine of x. And again, I hope anyone arriving at this video of mine is fluent with all those skills about finding derivative on most of the functions out there. Okay, so f prime of x is cosine of x, provided that our f of x is sine of x. And so after that, next step now is, the next big step now is I am going to obtain, okay, I'm going to get the equation, right, the equation of tangent line. Okay, and of course tangent line to f of x, okay, of tangent line at the easy point x equals 0, not 0.1, at x equals 0, the easy value again. So underline that for me. But then once again, when you're actually doing this on your own, then it should be a lot faster than my step-by-step careful instruction right here. All right, so that means the slope. So now into getting the equation of our tangent line at x equals 0, then the slope now is simply cosine at the easy value, 0. Okay, I'm substituting that easy value into the derivative. That gives me 1. The slope is 1. And so now I'm moving over to my other board, spend some time erasing it, and we're going to head out further. All right, so now once we've had the slope of the tangent line, then again, let's look for the tangent point. Our tangent point here, again, we're centering at that easy value, even though our real target is at 0.1, but our easy point is at x equals 0. And so if x equals 0, then the y value, I'm substituting this into the original function. So sine of 0, that gives me 0. So in other words, concluding our tangent point, it's actually 0, 0. That's our tangent point. Okay, and so now in that way, I am ready for my complete equation of tangent line. I'm using point slope equation again in this case. Y minus the y value of the tangent point, again, because I need to remind anyone, the tangent point stays on the line, on the tangent line, and stays on the graph, on the actual function. That's why I can use the x value given here, substitute into the function to find the y component of the tangent point. But now getting with the equation of my tangent line, I'm using that same tangent point again, and doing y minus 0, the y component of tangent point, equals 1, the slope, multiplied with, in parentheses, x minus 0. Okay, and now all of a sudden it's ready. Y minus 0 is just y. 1 times x minus 0 is just x. So this is our linearization right here. Now we can see this equation of tangent line as a function t of x. Okay, a function t of x equals x. 1x plus 0. Okay, so yes, once again, I'm using that term. This is our linearization right here. Our function sine of x can be approximated by a linear function. That's why it's called linearization. It can be linearized at x equals 0. Okay, so this is the linearization at x equals 0. All right, so now believe it or not, shocking or not shocking, but this is how it happens. Sine of 0.1. Now we're tackling down really at our target right here, sine of 0.1. Let's forget about using an actual calculator, because many calculators still do not in these days have an operation for a trig function. But this is approximately, substitute that into, I shouldn't use equal sign because we don't find the exact value. We say approximately the value that comes out from t of 0.1. But hey, t of 0.1, t of x itself is just x. So t of 0.1 is just 0.1. Okay? And so that means what? Sine of 0.1 is actually turns out approximately 0.1. Sine of 0.1 is approximately 0.1. And so now again, let me do a quick comparison here. All right, so back on my other board, I had to erase a lot of stuff so that I can make some space for myself here. But so now really let's use a real advanced calculator to get exact value. Okay, now I'm talking about exact value. And even see trig function, the reason I brought up this example because even using trig function and even trig functions came with your calculator, it's tricky in a sense that we got all that headaches about, make sure you keep your calculator in radians and in degrees. So now if I'm attempting to find this real value, this actual value on the calculator, then I have to make sure that I use this calculator for a lot of my calculation, but yours should have a similar functionality. But I gotta make sure I turn my calculator into into radians mode right here, because the problem here in the beginning I was saying that this value was in radians. Okay, and so now, all right, so in radians, sine of 0.1. My calculation came out to be 0.099833 and a lot longer. Okay, and look at our approximation. Using the approximation that we've had, using the linearization, using the linear approximation we've had, then sine of 0.01 is approximately 0.1. Look at how close we are. I mean, if I round this to simply 3 decimals, if I round this answer to 3 decimal as usual, okay, then this answer rounded to 3 decimal is we are forced down to 0.1 again if we rounded this to 3 decimals. And so then that's pretty much, we're boom, right on spot. Okay, and so now, not too many Calc 1 instructor mentioned this because it's kind of far away for you to feel this impact. But at some more advanced courses later on, yes, you will start hearing more people say sine of A is approximately equal to A itself. Sine of A is approximately equal to A. Okay, sine of 0.1. A, sine of 0.1 approximately equals 0.1, sine of A approximately equals to A, but not always, So I was not finishing with my sentence. So you will eventually hear a lot of mathematicians, a lot of physicists, a lot of advanced math students, maybe just by your Calc 3 level, then you will start hearing this a lot, but sine of A is approximately equal A for small a. Okay, for small a. And so it's a little bit abstract right here to say small a, but that's about the best the mathematicians can say. But the idea is, see, for values that's close enough to 0, because see, this problem is the origin of how it came out right here. See, for a value that's close enough to 0, then the sine function is close to this linear line right here, t of x equals x right here. And so for that reason, you don't need to take this. Right now, it's just something for you to know, okay? And it's not going to be it's very unlikely that any instructor in Calc 1 will test you with this understanding. But trust me, at some starting with Calc 3 and the later courses in math, depending on how far you want to go, then you will start hearing this a lot, especially in many of your physics applications. Okay, so the fact here is simply for small a means for values of a's close enough to 0, and of course we're looking at in radian units. Then the sine of a can easily be regarded as just a itself. Okay, so before I completely close down this example, let me quickly show you the actual graph right here for you to really understand what we were doing, because everything we did so far is completely based on the series of calculation, steps of calculation. Yes, you probably see enough repetition in the steps here, but now let's look at some graphical explanation to convince yourself. All right, so give me a moment to prepare my screen here. All right, so here's the graph right here. And now I'm going to adjust, and I'm going to bring the graph a little bit up. And so allow me for some rare instance like this. I am not going to put my x-axis in radian scale here. I'll just put it in, I mean, these are in radians. What I meant is I'm not putting my x-axis on the pi units right there, okay, in steps of pi, because I want you to understand where 0.1 is. So 1 is here, okay, and so pi is a 3.14 is about right there. See what I'm saying? So 3 is here in our regular scale right here. So now I'm putting on, all right, so this point right here. Now let me really zoom it in right there. Okay, so this point right here is our 0.1, and f at 0.1, sine of 0.1 is this value 0.0998 right here. So that's blue point, that's the blue point. And I really need to zoom it in even further. So this is 0.1, halfway between 0 and 0.2. And our graph here is the sine function graph. And I had to already zoom it in so much to actually see, to have a good visual of the point right there. So again, this is 0.1 comma sine of 0.1. And so now the easy value is here. Remember, we chose the easy value to be 0. And so now here we go. The easy value is that point right at the origin. Makes sense enough, okay? And now our tangent line, now in this case, this is our equation of a tangent line. Let me now put the equation of a tangent line together with the graph here. So in black ink, in black color, here's my tangent line. So now look at, I mean, even in a really close zoom right here, can anybody viewing this video tell me the difference, tell me whether this blue point is on the red line, is on the red curve, or on the black line right there? I mean, really we can't without my the previous explanation, okay? And I'm going to keep zooming it in. I'm going to keep zooming it in, and it still doesn't make much difference. It still doesn't make much difference. I can't even tell the difference, okay? And so now if we're substituting in, so I'm now going to substitute 0.1 into our function, into our linearization, into our linear approximation right here. So now all of a sudden I have a green point. But the green point and the black point are so, I mean the green point and the blue point are so close to each other that I have to zoom in very extreme level of zooming. Then we're going to start seeing some difference. See, so, and see, when we zoom in close enough, then we can't even tell whether this this red graph is a curve anymore, because it looks so like a straight line. Okay, this black one here is actually a straight line. It's a linear function. It's t of x equals x. But this, look at this, our sine graph. In a far zoom, it's a curve. It's a nicely bent curve. Okay, but when it's close enough, right? When it's close enough, then look at how close it is to being a line right here. And that tangent line came out from the center at x equals 0. Okay, so now anyone viewing my video and follow along with the example can have a sense about how effective this method is of using linearization, using linear approximation. And in the end, what I have just now convinced you again is that eventually it's not a big impact right now for as you are learning in Calculus 1, but take this with you. One day you will start hearing more people among your professionals say sine of A is approximately A, or sine of A is A. They can even get to that extreme extent right there. Sine of A is A for small a right here. How small? We don't really need to make judgment, and you saw that on the graph already. Okay, and that's the whole idea about how we can do the linear approximation.